This acne marketing decisions problem is that two-stage problem we were talking about yesterday at the end of class. They're trying to decide whether to market a new product. There's considerable uncertainty about whether the product will eventually succeed. They believe it might be wise to introduce the product in a test market before rolling it out nationally. So their first decision is whether or not to do the test market, because the test market's not free either. They assume the cost of the test market is $100,000, so that's how they collect their data, right? We assume this is mostly a fixed cost, so the same cost is incurred regardless of the test market results. If Acne decides to conduct the test market, they must wait for those results. Based on the results of the test market, it can then decide whether to market the product nationally, in which case it will incur a fixed cost of $7 million. So it's $100,000 for the test market and $7 million to roll out the product nationally. If the original decision is not to run the test market, the final decision whether to market the product nationally can be made without further delay. Acne's unit margin, the difference between the selling price and unit cost, is $18. We assume this is relevant only for the national market. Okay, so down here, Acme classifies the results in either the test market or the national market as great, fair, or awful. So in other words, the product could be great, it could be fair, or it could be awful. Each of these results in the national market is accompanied by a forecast of the total units sold. The sales values in thousands of units are 600 for a great market, 300 for a fair market, and 90 for an awful market. In absence of any test market information, Acme estimates the probabilities of the three national market outcomes to be 45, 35, and 20. In addition, Acme has the following historical data from products that were introduced into test markets and national markets. So, bunch of information, 3 paragraphs worth of information. Use the decision tree approach to find the best strategy. So, a lot of information. Let's try to draw an outline of the tree first, and then we will see what we need to do here. I got 2 of these. If you guys can stand it, I've got 2 of these Big Daddy examples to go through, and once we go through them, my new markers are over here. So what's the first decision we're making? Most decision trees are going to start with a decision. So what's the first decision we're making?
Whether to market a new product.
Okay, so whether to market a new product is partially correct. Whether to market a new product nationally or test. So which decision would you make first? Okay, right? So should we have a test market or no test market? Okay. Now, if we do the test market, let's make it simple. What if we don't do the test market?
The 100,000.
Then what? Are we done? That's right. You still can decide to go to the national market or not. By the way, you want to leave a lot of space on your paper for this tree. Okay. So we didn't run the test market, we didn't run the national market, and so are we done? We gave up on this product?
Yeah.
Yeah, right? We didn't do anything. We gave up on this product. We're done. There's no cost in that. We're good. If if we didn't do the test market, but we did decide to roll out the product to the national market, what can happen? I'm going to draw this slightly differently in anticipation for the need for space.
Sales could be great, fair, or
That's right. So the sales being great, fair, or awful, is that a decision that you make, or is that an outcome?
that's not.
That's an event, right? That's an outcome, right? So we could have great, fair, or awful. Okay? All right. So what numbers do we put where here?
1,000 for grade, 600 for.
Okay, yeah,
So
so
it's,
it's 1,000.
that's 600 for grade, 300 for fair, and 90 for.
Okay, so it's 600, 300, and what was it, 90?
90.
Yeah. So that's sales in thousands of units, right? And I think, what was our margin? It was 18, right?
Yes.
So this is 600 times 18. We'll just remember, everything's in thousands. 300 times 18. Actually, I'm writing these numbers in the wrong place, I just realized. Right? These are revenues. Let's make a side calculation, because we might use these numbers over and over. So 600 times 18, 48 plus 60, I want to say 1080. $10,800. 300 times 18, 5,400. Sorry. And 90 times 18, what do we got? 972, 1,620. Check that again. 90, 72, 9 times this 162, yeah, 0. Okay. So what we're saying is, if it's a great market, we're up 10. It's all in thousands. Fair market 5,400. Awful market 1,620. So the reason I don't want to write them on the leaves, by the way, is these are the paybacks you get when these things occur, right? These are the paybacks you get when these things occur. What about the costs of these decisions? Are there any costs in this branch we need to account for?
The 100,000?
Yeah, so we have a minus 7 million here. And since we're putting everything in thousands, I'll do minus 7,000, because we're truncating 3 zeros to make our.
The only cost because we didn't do the.
That's right, we didn't do the test market. So the final leaf has the total cost along all the branches added up, right? So this sounds like 3,800. This one sounds like minus 1,600. And this one sounds like minus, what would it be? 5,480. Okay, are we done with that whole entire branch? Missing one piece of information, I think.
Is this saying that you still have to pay the 100,000 per test even if you don't?
No, no. George is right. If we don't do the test market, there's no cost for the test market. But up here, we're gonna have to pay the 100,000, right? So minus 100. There's one piece of information missing. Can you see what it is? Great, fair, and awful. Probabilities, very good, Michael. What are the probabilities of a great, fair, and awful market?
45, 35.
That's right, 45, 35, and 20. Okay? That was the easy branch. What happens if we test market? By the way, these trees will have a sort of a common, sort of a standard type of structure that you'll get used to. You look at it carefully. So we run this test market. What happens next? I think it might say it up a little higher. It sort of says, if Acme decides to conduct the test market, it must wait for the test results. How do we model that in the tree?
To it?
Well, we have the cost for running the test market already there, right? We don't have to pay any cost for the results, and because we haven't sold anything yet, I don't think we get any profit from the results. But how do we model the results is what we're asking. What can the results be from the test market?
Oh.
600, 300.
No, those are the actual sales, right? Those are the actual sales values. We're just testing this
Like
to
what's-
see if people like it.
What's the outcome if we test? We
Yeah.
either make or don't? Or
Okay,
go
so is that what it says, make or don't? You're getting warmer though.
Or they don't.
Yeah.
Well, we're in the branch now where they do test. We already took care of the don't test branch. So if we run the test market, it says in the very top line, Acme classifies the test market or national market results as,
Great, they're all.
okay? So I'm gonna draw a great, fair, or awful. Is that a decision or an event? An event, right? So the test market could be great. The test market could be fair. Or the test market could be awful. All right? Now what? Suppose it was a great test market. Now what? Well,
The forecast.
well,
Now you stand with the data.
If it's great, then 1,000.
okay, very warm, Michael. So you're going to make some prediction. In other words, you're going to make some decision, right, about whether to market nationally or not, right? And again, if you market nationally, it could be great, fair, or awful. Okay, and we know the payoffs here, right? 10,800, 5,400, 1620, right? We know this is minus 7,000, right? In essence, this tree up here is the same as this little branch down here. What about if we get a fair test market?
300.
Okay, well, no, again, that's the test market. We don't know what the actual market's gonna be,
0.35.
right? We don't know what the actual market's gonna be, right? So, we just ran a test market, we got fair results. What's our next stage? Decide, right? So once again, same tree, market, nationally, right? Don't, right? End, great, fair, awful. $10.80, $5.40, $16.20. Same thing down here. Market nationally. Don't. Circle, great, fair, awful. Okay?
Try to delete them.
Pretty gnarly, right? 1080, 540, 1620. But there's sort of a natural flow to this thing, right? If you don't test market, you make the national decision right away, and then you see what happens. If you do test market, you wait to see what the test market told you, and then you still have that original decision, right? So you still have the decision of whether to go national or not. If you go national, of course, you are going to incur the cost of doing that, right? So this whole branch has an extra cost of -100 in it, but you get additional information for paying that -100. Now here's the big question. I got probabilities here, I got probabilities here, I got probabilities here, and I got probabilities here. We got a lot of probabilities. If I had a great test market, given I had a great test market, how do the probabilities of great, fair, and awful change? Given I had a great test market, how did these probabilities change? How would you think they would change? Right, these should go up, exactly, and awful should probably go down, right? So you can see we're going to need some Bayesian updating here, right? We've got a great test. Let's call this great test, fair test, awful test, right? We need to know what these probabilities are, okay? So I'm going to define some events. Great test, fair test, fair test, awful test, and of course we have great, national market, fair, national market, and awful national market. All right, as you might be, so what do we call these probabilities here? 45, 35, and 20? How do they connect to these events? Right? Really, remember how I said there's two sets of events, right? We got these, we got these. Right, instead of just two cases here, right, in and out, you've got three cases, so the probability, if you add the probability across all three, you should get one, right? So what's the 0.45, the 0.35, and the 0.20? What probabilities are those? We have them over here. 0.45, 0.35, and 0.20. Those are the prior probabilities, exactly, very good. So the probability of good is 0.45, probability of fair, 0.35, probability of awful, 0.20, right? You can see they sum up to 1, not surprising. those are the prior probabilities, right? If we don't have any additional information from our test market, all we can do is use our prior belief, right? Which is based on some kind of long-term historical performance of these products, right? What are these probabilities over here in this big old tree? This is the probability of a good national market given the focus group said the product was great, right? So this probability right up here on the very top is the probability of a good national market, or a great national market, given a great test market.
Ugh, there's gonna be like a billion of these.
Okay? Right? This probability is a fair national market given a great test market. And so on. We're going to do this in Excel, so we don't have to do it all by hand, right? Where do we get these numbers from? Well, we have a couple formulas, right? We have a couple formulas, right? And we have a bunch of information up here. Are they, do you suppose these numbers are just given up there? What do these numbers say? Of the products that eventually did great in the national market, 64% did great in the test market. What's that saying? It sounds like a conditional probability, right? Let's write it, now that we have our events defined, let's write down what that is. So what is that? Probability of,
Given the product is well national market,
which is, G, right? Of the ones that did great in the national market, given they did great in the national market, the probability it did well in the GT test market is 64, right? Of those that did fair in the test market, of those that did great in the national market, probability that it had a fair test market was 26. Of those that did great in the national market, the probability it did awful in the test market is 10.
And these are the likelihoods?
Indeed. Indeed. These are the likelihoods. And you can see I wrote down 3 of them. There's actually 6 more. Let's do one more. Second paragraph. Of the products that did fair in the national market. Right? Fair in the national market. Right? What's the probability it did great in the test market? Of the products that did fair in the national market, 18% did great in the test market. 0.18. Probability of a fair test market, given the product was fair, right? So again, this is that sort of historical data. 57%, and then 0.19 for probability of an awful test market, given it was a fair product. 19?
0.25.
2.5. Doesn't add up, right? And 3 more, okay? Conditioning on the awful, right? Dot, dot, dot. So we've got priors, we've got likelihoods, we want posteriors, exactly. Sounds like the perfect opportunity to use Bayes' rule, right? These are our things we're seeking, right? Because we're gonna pop these posteriors up here in the tree. Okay? I'll write down the formula one more time, right? The Bayes rule formula is this: A given B is equal to B given A times P of A over B given A times P of A plus B given A complement times P of A complement. Now that formula, Bayes' rule, right, is written as if there's just B and B complement, but here we have three events. So I'll write down the little more generalization version of this, right? Or maybe I won't. The numerator isn't going to change anyway, but my point is we're conditioning yeah, so my point is there's going to be, and because we don't have A and A complement, we have fair, great, and fair, awful, fair, great, fair, and awful, right? We're going to have three sets of variables in the denominator. So basically what I'm saying is we've got everything we need. We've got priors, right? We've got likelihoods. We can go ahead and use Bayes' rule to get these posteriors. All right, now we're going to move to the spreadsheet. So I'm going to attempt to remember how to do this. Okay, so in the spreadsheet, all the data is already given. We're going to make these calculations in a minute, and we're going to do it in such a smart way so that it's going to be rather cookbook. So you just have to be careful and enter the data correctly, right? So here's our priors, great, fair, and awful. And here's our likelihoods. Now, likelihoods of test market results along the side. So I'm going to help us a little bit and say great test, fair test, awful test. Make this a little bit bigger. So we've already written these likelihoods down. Can we put these numbers in here as they are supposed to be? So likelihood of test market results along the side given national market results. So I think what they're saying is this cell is a great test given it was a great product nationally.
0.64.
Is that 0.64 over there? Okay, 0.64. And then, oops, 0.64. And this one is great, fair test, given it was a great product nationally.
2.6.
Okay, 0.26 and 0.10. This is the next set. What's the next set?
18, 0.18, 0.18.
I'm sorry?
0.18.
Oh, 1.8, thank you. 0.57?
Yeah.
And 0.25. And these are the ones that we got a little bit lazy on writing down.
So it's 1 minus the both.
But we can check them, or we can do 1 minus the sum, it's true. Actually, we can't do 1 minus the sum, because actually these probabilities add down to 1, right? Because they're, right, if you had a great product, you were either a great, fair, or awful test, right? So you can't add them across. But they're given right here in the text, 9, 48, and 43, right? 0, 09, 0, 48, and 0, 43. Okay, so we haven't done anything yet. We're going to run Bayes' rule in 2 steps. All right? The first step, we're going to calculate the denominator here. Let me give you a tiny bit more insight on the denominator. This is what I was trying to be lazy about, but I'll show you how we get this. You can see it's going to be some kind of a sum product, right? So it turns out in this equation that the numerator is actually equal to P of A and B, and the denominator is actually equal to P of B. So this is a small aside, but this denominator, this thing is actually equal to P of B. This law, by the way, is called the total law of probability. So you're essentially saying in a Venn diagram, right? Here's B, and I'll make A like this, okay? So you can take the piece of B and you can say, give me the piece of B that's in A, right? That's the blue, right? P of A and B, right? Which is this term, right? Or you can say, what about the part of B that's not in A? Well, the not in A part, don't forget, is A complement, right? So the green thing here is P of A complement and B, right? So that's this piece. In our case, we don't have A and A complement, we have 3 pieces, right? So we have either great, fair, or awful. So it would look something like this. So P of a great test is going to be P of a great test and a great national market plus P of a great test and a fair national market plus P of a great test and an awful national market. And forgive me, but I'll take it one step further. Great test given great national market times P of great national market plus P of fair great test given fair national market, P of fair national market plus P of great test given awful national market plus P of awful, right? So it's the denominator but blown out into 3 steps, right? Anyway, that looks just like a sum product thing, so we can easily do that. So essentially what I'm saying is, here's the P's of great, fair, and awful, right? And right here, this is the probability of a great test given a great national market, a great test given a fair national market, and a great test given an awful national market. So we can take this range and sum product it with this range, and we'll get the probability of having a great test, right? So I'm going to relabel this too, great test, fair test, awful test. We did this yesterday in the drug example, but it wasn't totally clear. So let's run this sum product, and you got to make sure you anchor these. What did I do wrong? Oh, forgot the parenthesis. You got to make sure you anchor these. But not these. Now, I didn't talk about it, but this unconditional probability of a great test, this value is going to go right on this spot right here. Because a priori, we didn't know how often we got a great test. And we're also going to use it in Bayes' rule. So it looks like we get great test about 36.9% of the time, we get a fair test 41% of the time, and we get an awful test 21.85% of the time. So essentially what we're doing is we're calculating the denominator of Bayes' rule. Now we're going to do the numerator next to get the posteriors. So I'll write in the values that we just calculated into our tree. This one is 0.4125, this one is 0.2185, and this one is, whatever it is, 0.36.
269.
All right, and now the last step. This involves some tricky anchoring, so let's be careful. So we have to multiply. So I'm using this, the one we just calculated for the denominator. I'm up in the upper left-hand corner. We have to multiply P of great test given great market. I'm going to leave that one alone, times the prior probability. I need to anchor this on row 17, and we're going to divide that by the denominator that corresponds, and I'm going to anchor this on column G. So this is I was mentioning yesterday, there's a cookbook way of running Bayes' rule, right? As long as you get the data into this table correctly and you follow this process, you're gonna be doing fine. Again, the tree, it looks really complicated, but if you think about it, it makes sense. On the lower half, we're not making any test marker, we're gathering no additional information. On the top half, we are running the test market, so given the test marker results, we want to find out how likely is it for great, fair, and awful real market. So if you entered that formula correctly with the right anchoring, you should be able to copy it across and down. And now we should be able, let's check this, we should be able to sum across and get 1 in each of these 3 cases. So it's looking good. Okay, just have to make sure you have your anchoring correct. So what we're saying is, for example, if we have an awful test, let me change the labels here as well to make it clearer. Copy these 3 labels down. If we have, let's start with great. If we have a great test, there's a 78% chance we're going to have a great market. And there's a 17% chance we're going to have a fair market, and approximately a 5% chance we're going to have an awful market, right? So these are the posterior probabilities going across now. If it's a fair test, then the great market is 28. The fair market is 48, and the awful market is 23. That doesn't really add up to 1, I know, but that's because we left off the fractions. We won't do that in Excel. And if it's an awful test, then the probability of a great market is 20 or 21. Probability of a fair market is 40. And the probability of an awful market is 39. Okay? Questions? Let's suppose you missed the boat at some stage. I will give you this completed version of this. My laptop went to sleep though.
that it? Did we finish that?
We're done.
Oh my gosh,
Yeah,
that was cool.
yeah. It was a lot of explanation, but the actual calculations weren't that complicated. All right, let's see here.
So what's the deal with the weird anchoring? Because that confused me.
Yeah, so essentially, when we run this formula, let me do this to maybe help you. Let me write the actual formula we're doing. It's all sort of insight. Let me give you the actual formula here, if I can fit it in the formula. We want to know, for example, we want to know what the probability of a great market is given a great test, or any combination, right? So what this is great test given great market times the probability of great market on the top, and the denominator is same thing, same term is always in the denominator. But then you also have the probability of great test given fair market times the probability of a fair market plus probability of great test given awful market times the probability of an awful market. So that's what I meant about having three terms in the denominator. Now the denominator we already computed with this sum product. Okay, so we already did the denominator. So what you want to do is you want to grab the conditional probability in the numerator from here, and that's going to change every time you copy it in this matrix, right? You want to grab the prior probability for the numerator, and when I copy it down, I don't want the row to change, but when I copy it across, I want the column to change. So that's why I'm doing one-way anchoring on that, right? I don't want the row to change, but I want the column to change. And then G16, I want the row to change, but I don't want the column to change. So that's why I'm anchoring that way.
Okay.
You tend to do one-way anchoring a lot when you build tables, where you use information from the margins in the table. All right, so promising you the partial results here. Let's get them up. Who wants to build this tree and tree plan right now?
Sure.
All right, well, it's going to be fun. It's going to take some minutes. Do you have your tree plan thing running somewhere? It's hard for me to get mine running again. Okay. Here's the file. It's uploaded, the file with the calculations that we just made. Now, here's my recommendation once again. If you're going to do a tree plan, start in column, kill this text here, kill this little text box, and start in column H or I or J.